Hey, this is Leach with Simpson Math, and in this video, we will be continuing our discussion with conic sections with the parabola. Last time, with the parabola, we talked about how we could define the parabola as the set of all points that has the same distance from a point, which we call the focus, and the same distance as the distance to a line called the directrix. So it's a set of all points such that we have that has the same distance to a point, the focus, and to the directrix, which is a line. So every single point on this parabola, if I was to draw a line from the focus to it and then perpendicular down to the directrix, it would be the same distance. That's what a parabola is. So a little bit more information about this focus and the directrix. So the vertex, which is that turnaround point in the parabola, it is the midpoint between the focus and the directrix. So since we have that, and we can define that vertex as hk. That's a familiar naming system, where h is how far we move it horizontally, and k is the distance we move it vertically. You should have seen something like that in your transformations class. Maybe instead of h and k, maybe they referred to that as c and d, but it's the same thing. So back in college algebra, you likely saw that. And so then the distance from the focus to the vertex we call c, as well as the distance from the vertex to the directrix we call c. Because remember, the vertex is the midpoint between this focus and the directrix. So this total distance here is 2c. So the focus is always inside the parabola, while the directrix is always like outside the parabola. So we have this focus that's inside the parabola. It is c, has a distance of c away from the vertex, and then the directrix was on the outside of the parabola, which is c, a distance of c perpendicularly away from the vertex. And then all lined up, the focus, the vertex, and then perpendicular to the directrix is that axis of symmetry. So that's our parabola. That's what we're going to be dealing with. You might be asking yourself, what is that c? Well, hold on one sec. And one note is that all the above definitions hold true whether we're talking about vertical or horizontal parabolas. So we have, like I said, vertical and horizontal parabolas. This formula should be pretty familiar from your college algebra days. We have y equals a, x minus h squared plus k. Like I said, instead of h and k, it might have been c and d, but we are using h and k here. It does the same thing. Then, if I wanted to, I could expand this. I could multiply this binomial squared out and get this perfect square trinomial. And so we should know how to quickly do that. We square the first, multiply them together and double, and square the last. And then we get this perfect square trinomial. We can distribute the a, and then we can gather up our like terms, and I'm going to move this y over. And we should notice that we then have four like terms, four sets of different terms. And I could look at this x squared term and basically simplify this leading coefficient into just a capital A. I could simplify the coefficient in front of the x as just capital D. I could simplify this this coefficient, this is regular coefficient, that negative one as e, and all of this constant, there's no x or y on here, as just f. And notice this is the general form. Now, these relationships aren't things you need to learn or remember. That's not necessarily a hard, fast relationship between these lowercase and uppercase letters. Just the point here is that I can have something in standard form, expand it, combine like terms, and end up with something in the general form. The same thing could be said if I start with something in the general form, I could then complete the square and end up with something in the standard form. So looking over here, we have this horizontal parabola, and last time we talked about this general form, so you could complete the square with the correct substitutions and end up here with this horizontal form. Another way of thinking about the relationship between the two standard forms is that think back, if you weren't restricted to functions. If I have a quadratic and you inverse it, it won't be a function anymore, but you could express it in this manner, where literally we just switch x and y. We switch x and y, and then when we do those solvings and manipulations, remember everything about our function, everything about the inputs switch, right? Our inputs become our outputs, our verticals become our horizontals. So notice my H's and K's have switched places as well. And in some ways, this could almost really be a B. If you think back to your transformation where B is your horizontal stretch and A is your vertical stretch. But in Conics, you'll see that we'll be dealing with A's and B's in different ways, that we're not restricting them to be a horizontal stretch or vertical stretch or whatever. So I'm just going to stick with it just being an A because I don't need to muddy the waters up with another letter today. So we have our horizontal and vertical, oops, drew a line through it. We have our horizontal and vertical standard form formulas. Or also you might have just thought of this as your vertex form back in college algebra. And then we have our general forms that we talked about last time. So going back to what I talked about a second ago, so we have basically our definition of our parabola in terms of this focus and the directrix. And we have these two different forms. Specifically today, we're going to be looking at this standard form a lot. So you might be wondering, what is the relationship between those two? Well, to define it, one way that I'm going to do this, I'm going to do it first visually with you. I'm going to head on over to Geogebra and show you the relationship between our A and our C. So I'll see you there. All right, over here in Geogebra, I've already constructed this document where we have our a parabola that I've defined where I have a focus at 0, 0.25, and my directrix is at y equals negative 0.25. And the parabola that goes through that should look very familiar. It is our parent function parabola. If you take a look at the points, we have the point 0, 0, 1, 1, 2, 4, and there's symmetric points on the other side, negative 1, 1, negative 2, 4. So this is our parent function parabola. So I'm going to zoom in a little bit and want you to see something that I've defined for us. Well, we have C, where C is the distance from the vertex to the focus, and it's 0.25 or 1/4. And notice if I go down 1/4, I'm at the directrix. If I go up 1/4 from the vertex, I'm at the focus, which fulfilled what I talked about a second ago. And then if you recall from parabolas, if you go over 1 unit, the amount that you have to go up or down from that 1 unit to get to the function always is your A value, always and forever, because your parent function is 1, 1. So whatever you multiply that y value of 1 by is your A, so whatever that height is actually your A. Well, looking at this parabola, we can see that C is 0.25 and A is 1. And you might think to yourself, well, C is 1/4 the size of A, and that is true, but that's actually not always going to be true. If I just move C just slightly, you see that that's not the case. But something you should notice about C is that as I move this around, as I change C and A changes with it, if you look in the bottom left-hand corner, you'll see that there is, I'm multiplying A times C, and as I move A and C around, it is always 0.25. So let me just stop it somewhere. Doesn't really matter where. And so here A is 0.7692. If you multiply that times 0.325, you'll get 0.25. The same thing is going to be true with your directrix. If I move my directrix around, I'm going to end up with A's and C's again. Let me just zoom out and let me see if I can rotate this just to show you. Even if it's rotated funky, so the distance of this C, 1.3141 and A is 0.1902. Multiply those together, you're going to get 0.25. This works for, like it's a diagonal parabolas, which we won't be studying in this course, but they do exist. Here's a horizontal parabola, which we'll be looking at later. And so with this, our C is 0.25 and our A is 0.1. That definitely multiplies to 0.25. I can swoop it around to over here. And that multiplies to 0.25. This is A times C is 0.25. So I don't care where I put this, A times C is 0.25. So from GeoGebra, we saw that A times C is 0.25 or 1/4 for all parabolas. Therefore, we can have this interesting relationship and we could define A as 1/4C if I just divide both sides by C. And then I could do the same thing with C. If I want to know what C is, I could just divide both sides. I could divide both sides by A or multiply both sides times 1/A, and I end up with 1/4A. So this is a very handy relationship to know the relationship between A and C. So if you're like, oh, okay, Mr. Leach, that was a little bit dubious proof there, just using GeoGebra. There's just a geometric proof. But I want to see that algebraically. Well, here it is. Feel free to pause the video, take a look at this, or they are in my notes online. You can take a look at this algebraic proof where we just start with a point and a line and the definition of the parabola with it being the distance from both of those. And if you add them up, they're the same. So if you follow through this proof, you'll see that they that we end up with 1 over 4c equaling our A in our vertex form. So feel free to take a look at that or just trust me. All right, so now let's take a look at this next, at our first example. This is going to be very similar to what you're going to be doing on your homework and tests and stuff. So with this, I'm going to give you a parabola. It'll probably be in just the general form, and you'll have to convert it to the standard form or the vertex form using completing the square. And then we'll answer these things. So we'll find the vertex, state the A, find the C, which we call the focal length. Give me the coordinates of the focus and the directrix, X and Y intercepts, and then we'll ultimately be graphing it. So let's take a look at this example. So we have x squared eighths minus x halves minus y plus 3 halves equals 0. So first, from last lecture, you should recognize that this is a conic. We have, but we only have one squared. Since we only have one square, it's a dead giveaway that this is a parabola. So let's convert this into standard form by completing the square. I don't want to mess with these fractions because you gross, so I'm just going to multiply everything times 8. I actually do over here on the side. I'll show it to you in a second. I work with a fraction, so I'll show you that in a sec. But I can multiply everything times 8. So now I have x squared minus 4x minus 8y plus 12 equals 0. I can do this because this is an equation. If I was completing the square and I just had an expression, I would not be permitted to multiply everything times 8. I would have to work with the fraction. But because this is an equation, I can do that. All right, so we multiplied everything times 8, and now I can complete the square. First, before I did that, I did add 8y over to the other side, because in my standard form, it is y equals or x equals, so just move this single linear term over. All right, so then now I'm going to take this minus 4. I'm going to half it and get negative 2, square it back and get 4. And so I just added 4 into this equation, so this has to be balanced. I don't need a constant over here on the right-hand side, so since I added 4, I'm going to then in the same exact step subtract 4. So really all that I've done between these two things is just add 0. Plus 4 minus 4, that's just 0. So I haven't changed the value of the problem. If I didn't want to add it there, I could have added a 4 on the right-hand side, but that would just take more solving manipulation later. All right, so the 12 and the negative 4 give me 8. And so I have x minus 2 squared plus 8 equals 8y. And then in order for me to solve for y, I divide everything by 8, and I end up with y equals 1/8 times x minus 2 squared plus 1. So this should feel very familiar. You could have graphed this in college algebra. Our vertex, right off the bat, you should know is going to be at right 2 up 1. And I have a little bit of a sketch going over here where I just go right 2 up 1 just to think about this. Since my A is positive, I know that I'm opening up from that right 2 up 1. And then it's a 1/8, so I drew it really wide because I know that that's a vertical compression or vertical shrink. So it makes it feel really fat and wide. It's gotten squished down. And then since it's opening vertically because this is a vertical parabola, because it's this x is being squared, then I have a vertical axis of symmetry, and it takes on the same value as our x value in our vertex. So this is just x equals 2. If you want to write it generically, it would just be x equals h when it's a vertical parabola. All right. Sometimes I know I have part C is for you to determine whether it opens up or down and all that jazz first, or all that jazz second. I like to sometimes think of that first. So as soon as I see this, I actually think, oh, this 1/8 It's a vertically opening parabola that's been squished down. It opens up. It's going to have a minimum. I sort of kind of make those thoughts first before I deal with the axis of symmetry and vertex and all that. Another observation you might even notice right off the bat, because I've gone right to up 1 and then have this upward opening parabola, you should almost already notice that the parabola does not cross the x-axis. There are no real roots, there are no x-intercepts to this parabola, which will come in handy a little bit later. All right, now to the new part. What about this C business? I'm going to need to graph my focus, so where do I do that? Well, remember, A times C is 1/4. If you remember that A times C is 1/4, then you can get these two different formulas depending on if you need to know A or C. We're needing to know C in this case, so it's just going to be 1 over 4A. So I plug in my A, which is an eighth. 4 times 1/8 is 1/2, and 1 over 1/2 is just 2. So that means that my C is 2. So when I have my parabola here, I have this vertex. I said earlier that the focus is always inside the parabola. So I just need to go up 2 units to get to my focus. Now, I don't mean to insult your intelligence or anything like this, but in the years that I've taught this, for some reason, students freak out when it comes to dealing with this. They want formulas. They look in their textbook or they look online and they see these lists of all these different formulas. Like if the parabola is opening up, you have to do this. If it's opening down, you have to do this. You end up with it seems like 20,000 different little microscopic formulas to deal with. No, that's craziness. Okay, so just imagine that you time traveled back and you encountered your fifth grade self. In 5th grade is when you learn the coordinate grid, or at least it was when I was in school. So in 5th grade, you learn the coordinate grid, and imagine you tell your 5th grade self, "Oh my gosh, I'm so glad I ran into you. You just learned the coordinate grid system. I need help. So I have this point 2, 1, and then I moved. I need to find the point that is 2 units above that vertex. So if I move that vertex up 2 units, where am I?" Now, your 5th grade self is going to look at you like you're crazy. They're like, why are you asking me this? You're in college and you're asking me if I move my point 2 units up, where is it now? Dude, just add 2 to the y value and now you're there. All right? Now, like I said, I don't mean to insult you, but I promise you, if you start nosing around and seeing formulas, there's a lot of them, and they're just dumb for no reason. It's dumb to include all those because students will start overthinking it and freak out. They get paralyzed with fear about which formula to use. So just trust me. Just think about this. The focus is above the vertex. Since the focus is above the vertex, I need to move from my vertex up 2 units. So then this y value is going to be increased by 2 units, and we now have a focus at 2, 3. It truly is that simple. Then the directrix. The directrix is below the vertex. So I'm going to have my vertex, and I'm going to go down 2 units. So I have this horizontal line that is going through my y value. Anytime you graph horizontal vertical lines, look at which axis it crosses over. It's crossing over the y-axis at -1. So it is y equals -1. So my directrix is y equals -1. Now, as for our x and y intercepts, you can pick the general or the standard form. I'm gonna not pick the general form, and I'll just use the standard form in this case. Some other cases it might be easier, but let's probably just use the standard form in most cases. All right, so let's find our y-intercept. Just to note, conics aren't necessarily functions, so there can be multiple y-intercepts, so be aware of that. So for my y-intercept, we're going to let x equals 0, solve for y. So x is 0, solve for y, and we end up with getting 0 and 0, 3 halves for our y-intercept. For our x-intercepts, they are our real roots, so we're going to let y equals 0 and then solve for x. Now, we already know from our graph above, or also just from our knowledge about their vertex and the direction of opening, that there are no x-intercepts. But nonetheless, let me just, for completeness, solve and show you. So I'm going to plug in 0, then I subtract the 1, multiply by 8, and I'm at -8. So when I square root -8, I now have a square root of -8 that is not a real number. If you want to keep going, that is going to be an I square root of 8 or 2I square root of 2, and then I could add the 2 over, and it's 2 plus 2I square root of 2 are the roots to this quadratic, but there are no x-intercepts. All right, so let's get graphing. I do find 2 additional points. I find 1 and 9/8 and 2, -2 and 3. So you can use those points, and also remember, use symmetry. I plugged in this point, and I can use axis symmetry to find the others. So let's take a look at this. So I have my vertex at 2, 1. Then I went up 2 units, and I have my focus at 2, 3. I have my axis of symmetry at x equals 2, and that's this vertical line. I go down 2 units from my vertex, and that's my directrix, y equals -1. Notice how I have these labels everywhere. Every point, every line, everything needs to be labeled. All right, then I've graphed my y-intercept at 0, 3/2, and then I can graph a symmetrical point on the other side. That's 4, 3/2. And then I plugged in a 1 and got 9/8, and then I can do that a symmetrical point on the other side and get 3 9/8. I can plug in -2, and I go up to 3, and then I can do a symmetrical point on the other side. Little teeny tiny, just extra bit of information. This is TMI for most of you, but if you're curious, you want to know one more layer of things that I'm not going to be testing you over. There's something called the lattice rectum. Yes, you probably heard that right. Lattice, like a thing that vines climb up, and rectum as in the body part. So it's called the lattice rectum, and it's the distance across the parabola that goes through the focus. And what's special about it is that it is 4 C units wide. And so that means that from the focus to the other edge is just 2 C units. So in this case, notice that's 4 units. Over here, that's another 2 C units, which is 4 units, or completely across is 8 units. That's all that there is to that. It's not that big of a deal, so I'm not even going to go into it except for what I just said. But this is just an FYI. That's called a lattice rectum, and that's the length. That's just literally just the length of it, and it goes from here to here. So it's an easy way to get a few additional points if you're aware of that. And it sort of kind of helps you understand the buffer between our focus and then to that side. So then I graphed all my points. I did my symmetry point. I even wrote down what it equals, and then swooped the dots very carefully. And there's your parabola. Before I leave that first example, I wanted to go back and show you how optionally, instead of multiplying everything times 8, you could just factor out the 1/8. So here I factored out the 1/8, and then I'm left with x squared minus 4x plus 4 inside. We do complete the square process. Half it, get the -2, square it, get the 4. But then I'm not actually just adding a 4. I'm adding, 1/8 times 4 is a positive 1/2. So in this completely, if I was to FOIL this out, at this over here, I'm adding a positive 1/2. So if I'm adding a positive 1/2 here, then I'm really needing to counterbalance that and add in a negative 1/2. So that way I'm really just adding 0. So add in a positive 1/2 and add in a negative 1/2, which is 0. And then 3/2 minus 1/2 is 1. And that's actually quite a bit quicker than what we ended up doing while not dealing with the fraction. But that's how you can do that. So you can either multiply out the fraction basically, and then put it back by dividing, or you could just factor it out and deal with it. All right, let's take a look at this last example. Just a note here is that, like I said earlier, I like to think about the A and the direction that it opens before I deal with the vertex and the equation of the axis symmetry. Just helps me, I can wrap my head around what's happening with the parabola when I analyze this A before dealing with that B. All right, so here we have -2y squared minus x minus 8y minus 7. So when thinking about the general form of the conic section, this is not an ellipse, it's not a hyperbola, because we only have one square, has to be a parabola. When you see one square, dead giveaway, it's a parabola. All right, so it's a parabola, but what is being squared, the x or the y? Since it's the y that's being squared, I know that it is a horizontal parabola. It's going to open either to the right or to the left. And actually, since I know that it's a negative a, I know that it's going to be opening to the left. It's going to be a parabola that's like this because it's a negative a. All right, I'm going to take this x, add it over to the right-hand side so to get it out of my way. And then we're going to need to complete the square. So in order for me to complete the square, I need to factor out this -2, which I realize I didn't explain that in that step to the side. Bad me. I'll do that. I'll fix that later. So I factored out this -2, and then let's complete the square. So I am going to half the 4 and get 2, then square it back and get +4. But I'm not actually just adding in a +4, I'm adding in a -8. So collectively over here, there's actually a -8 that I'm adding in. So if I'm adding in a -8 here, I need to then add in a +8, so that way I end up with just a 0 for really what I'm adding in. So then combine like terms, and then technically we're factoring from here to here. So I'm finished my complete the square, and I flip my x over to the other side because it's just like it over there. So we say x is -2 times y plus 2 squared plus 1. So like I said, let's jump to go ahead and be thinking about my a. My a, like I said earlier, is -2. So it's going to be a parabola that opens to the left. The vertex is going to be at the rightmost point. And we can think of it as being horizontal. So when it's like that, I'm going to have a axis of symmetry that's horizontal. I'm going to have an axis of symmetry that's y equals, right? And the other layer for my vertex is this is not h and k. This is not horizontal shift, vertical shift. This is the vertical shift with the y and the horizontal shift that's outside. So this 2 is actually my my y component, because it's friends with a y here. Remember, you have to basically change the signs for inside the function. And then we have this 1. That's that's the x part. So it's the h comma k. And just understand that in the formula, basically, that there is this negative that's just there. So that's where you can think of just changing the sign. So our vertex is 1, -2. So let's find our c. So I'm going to do 1 over 4a, and my a is -2. So it's 1 over -8, so -1/8. When it comes to thinking about your focus and your directrix, remember the focus is inside the parabola, the directrix is outside the parabola. So my focus is to the left of the vertex, my directrix is to the right of the vertex. So if you were to tell your 5th grade self, hey, I have this point, 1, -2, and I need to move to the left a little bit, what would I change, the x or the y? Your 5th grade self would be like, you're crazy, just go to the left. So let's just go to the left. So go to the left 1/8, versus for our directrix, we're going to go to the right 1/8, and we'll just the x then instead of the y. One other little layer is, yes, this is a c that's negative. That's a little bit of an extra giveaway because that c does give us distance and direction. So it's a distance of 1/8, but that negative that's here is also a little bit of a giveaway that we're going to be going to the left. That's because the a does have a positive or negative to it. In our previous example, we had a positive a, so the c was positive. So when I added the c, I would just go up. So basically, add the c to the focus, subtract the c from the vertex to get your directrix, or from that corresponding part. All right, so we have a focus at 7/8, -2. I'm going to just go left just a teeny tiny bit. My directrix is at the vertical line, x equals 9/8. When I go right just a teeny tiny bit. All right, for my x and y intercepts, let's do the x-intercept first. We just plug in a 0 for the y, and we solve them down. It's actually quite simple this time because our x's and y's have been switched, so there's no great solving. It's just evaluating this right-hand side, and we get that x is -7 when y is 0, so -7, 0. For my y-intercept, it has the same level of involvement of finding your roots in a normal polynomial, or parabola in this case. So we're going to set the x to be 0, like always, but it's in a different position. So I need to subtract the 1. We get a -1, but fear not, because we're going to divide both sides by -2, and we get a positive 1/2. Then we square root, so I have plus or minus the square root of 1/2. And then I'm going to rationalize this. If I square root, let me rewrite this bigger. If I have square root of 1/2, this is the same thing as square root of 1 over square root of 2. Well, square root of 1 is 1, Square root of 2 is, well, square root of 2. And then we can rationalize it. This is pre-cal. You've been doing this for a long time. You've been rationalizing 1 over square root of 2 for a while. So this is square root of 2 over 2. And so it's a little bit friendlier to write the minus in front and the plus or minus in between. So it's negative 2 plus or minus square root of 2 over 2 is my y-intercepts, plural. We have 2 y-intercepts this time. Remember, most of these conics are not functions, so this is okay to have 2 y-intercepts. Just a reminder that square root of 2 is about 1.4-ish. So square root of 2 over 2 is about 0.7. So this is a negative 2 plus 0.7 is about a negative 1.3. Negative 2 minus a 0.7 is about a negative 2.7. So let's graph it. So I have my vertex at 1, negative 2. I have my focus just barely over an eighth at 7/8, comma, negative 1. And my directrix is this vertical line at x equals 9/8. Little compact tight thing. Remember that term, that lattice rectum, there's actually this distance right here is a, from here to where it should be, if I graphed it right, didn't quite, but there would be that quarter, 1/4, and that'd be 1/4, or a total of 1/2 right here. All right, then we get our y-intercept at 0, comma, negative 2 plus square root of 2 over 2. Notice I wrote the exact term, so that's about a negative 1.3. This is about negative 2.7, but write the exact term. So there's my y-intercept. All right, then I have my x-intercept at negative 7, 0. And then I can get a symmetric point, which, oops, I did not label. Let me fix that. I've labeled my equation here, labeled my axis of symmetry. It's y equals a negative 2 because it's crossing over the y-axis at negative 2. And this, like I said, this vertical line for the directrix is crossing over the x at 9/8. And then I found just one more point. I could have plugged in 1 to try to find this point, but I actually used my knowledge of parabolas, that if I'm stretching it 2, that if I go, like in this case, up 1, it would go over 2, so I knew that I would have a point here. Or I just easily just plugged in a negative 1 for the y value, and I easily got that an x was negative 1. So negative 1, negative 1, and then use symmetry to get the point on the other side. It would be negative 1, negative 3 for that point. So there we have it. There's our parabola graphed. You need to have, when you graph, you need to have your vertex, your focus, your directrix, your axis of symmetry, your y-intercepts or intercepts, any of your x-intercepts, and then with these functions you can have symmetric points. And then it's good to probably include maybe one extra dot or so that way you can get a good graph. So there you have it. There's a conic section parabola. Now you know what the relationship between A and C is, how to graph the focus, how to graph the directrix, and how to put that all together with a graph that you already knew with that parabola. I hope this helps, and I'll see you in the next video.